Welcome to ONT Lab number 3. Here in ONT Lab number 3, we're going to be taking a look at configuring header compression, specifically class-based header compression, both for TCP packets as well as for RTP packets. Taking those layer 3 and layer 4 headers and logically squeezing them down so that we preserve that very valuable WAN bandwidth. We're going to start out by seeing the theory of header compression. How is this working behind the scenes? Then we will take a look at a phone call going on right now. We will see how much bandwidth is being consumed by that single phone call. That's our baseline. And we're going to see it's probably going to be on the order of about 24, 25, 26K, something along those lines, for a single phone call before we turn on header compression, because we are using the G.729 codec. And by the way, when we turn on header compression, we can do this in a couple of different ways. On one of our routers, we will configure class-based header compression. The ability to use a class-based approach, in other words, use the three-step MQC process, became available in iOS 12.2.13t. We will do that on one router on one side of the link. On the other router, at the other side of the link, we will instead turn on interface-based header compression, because we may have an older router in the network. That older router may not support class-based header compression. We may have to use interface-based header compression. Fortunately, these two different methods are compatible with one another. Then, once we have turned on header compression on the routers on both ends of a link, we will measure the bandwidth being consumed by that voice phone call, and we'll see how much bandwidth savings we have. But first, let's see how header compression is working in theory. Right now, I have a phone call going on between the two analog phones that you see on screen. And R1 and R2, they are interconnected by a low bandwidth link. It's only running at 128 kilobits per second. That would be a good candidate to turn on RTP header compression. What we want to do is go into R2 and turn on class-based header compression, and we'll go into R1 and turn on interface-based header compression. But how is this really working in the background? If we think about a voice call, it uses RTP packets, real-time transport protocol packets, to send the voice information. And if we look at the IP header, the UDP header, and the RTP header combined, grand total, that header size is about 40 bytes in size. The payload is typically only about 20 bytes in size. We have a header twice the size of the payload. That is not an efficient use of bandwidth. What we can do is turn on header compression to help us out. And the compression ratios we're going to get are pretty impressive. We're going to go from about 40 bytes of header down to only 2 or 4 bytes of header. How is that possible? We're talking about 20 to 1 or 10 to 1 compression ratios. Here's the logic of header compression. Header compression says, consider a packet that's going between routers R2 and R1. If we look at every single packet in this voice stream going from one phone to the other, we're going to notice that the header information in these packets is very similar. As an example, if we look at the headers of these packets, we will notice that every packet seems to have the same source IP address, the same destination IP address, the same source and destination UDP port numbers, the same RTP payload type, which could be used to indicate things such as what codec, what coder-decoder are we using. Instead of sending this redundant information in every single packet, don't you think it might be more efficient if we just made a copy of those headers and put that copy of those headers in the routers at each end of the link? In other words, we're caching the header in each of the routers. Then we could send a much smaller header. What would be contained in this much smaller header? One thing we could find is something called a CID. That stands for a Session Context ID. Because if we had more than one phone call going on between routers R1 and R2, and we received a compressed header, since it was lacking the IP address information and the UDP port number information, it might be a bit difficult to tell what phone call this packet was a part of. That's what the Session Context ID can do for us. It can identify which voice flow this packet is a member of. Something else we might find is a UDP checksum. That's typically what we find on Cisco equipment. And remember, we said that we would be compressing from 40 bytes down to 2 bytes or 4 bytes. If we are using UDP checksums, our resulting header is going to be 4 bytes. If we're not using UDP checksums, the resulting compressed header will be only 2 bytes. Let's take a look at the syntax that we'll use to set this up. Remember, we will do this in a couple of different ways. We will configure class-based header compression, which uses the 3-step MQC process. To do that, in policy map class configuration mode, we're going to say compression header IP RTP. But realize, instead of saying RTP, we could alternately say TCP if we wanted to compress TCP headers at this point. In fact, we could just say compression header IP and both would be compressed in that situation. But in our situation, we're interested in a voice call. We want to enable class-based header compression with that command. But on the other router, at the other end of this link, we want to run interface-based header compression. Let's imagine that router is running an older version of iOS, prior to 12.2.13t. To turn on header compression in that environment, we could say IP RTP header hyphen compression to turn on RTP header compression on an interface by interface basis. If we wanted to turn on TCP header compression, by the way, we could say IP TCP header hyphen compression. Let's jump back to our topology real quick. Let's examine where we will enable each header compression method. Router R2, that's the router that we want to enable class-based header compression on, and router R1, that's the router that we want to enable interface-based header compression on. Let's go out to our routers and set this up. Beginning over on router R2, let's see how much bandwidth is currently being consumed by this voice call. If I do a show interface serial 0/0, let's take a look at how much bandwidth is being consumed by this voice call. It says 25 kilobits per second of bandwidth is being used on average going into and also out of this interface. That 25 kilobits per second, it is almost entirely made up of that voice call. And I admit there may be a little bit of overhead, a little bit of CDP traffic, maybe a tiny amount of EIGRP traffic. But for the most part, that 25K represents our voice call. That's the before, that's our baseline. Let us now go through the 3-step MQC process to turn on class-based header compression on router R2. Then we will go over to router R1 and turn on interface-based header compression. But from router R2, we go into global configuration mode and we say class-map, and we give a name for our class map. And here's a naming convention that I like to use. When I'm coming up with a name for a class map or a policy map, I like to use all uppercase. Let me call this class map C-voice. By using all uppercase, if I see this C-voice later as I'm looking through my configuration, I immediately realize that this is the name that I came up with. This is not some sort of an iOS keyword. This is a name that I made up myself. And I put the C to indicate that it is a class map. In class map configuration mode, let's recognize our voice packets. We can do that by saying match protocol RTP. RTP, the real-time transport protocol, carries voice traffic. However, RTP could also be used to carry video traffic. I want to make sure that I'm just talking about the voice packets right now. So I want to say match protocol RTP audio. Match protocol RTP audio. That is step 1 of MQC. In step 2 of MQC, we create a policy map. And sticking with my naming convention, I'll use a P to indicate that this is a policy map. And in uppercase, we'll call this P-voice. Then we go into policy map class configuration mode for the class we just created, which was C-voice. And we turn on header compression. We want to say compression header IP. And remember, we have a couple of options. I could specify that I only want to compress RTP headers for my voice packets, or possibly video packets. Alternately, I could say that I want to compress TCP headers, maybe for telnet packets. And if I just pressed enter at this point, it would turn on both RTP header compression and TCP header compression. But in our example, we are interested in RTP header compression. So let's say compression header IP RTP. That is step 2 of MQC. In the third and final step of MQC, we want to go into interface configuration mode for interface serial 0/0 and apply this policy map. We do that by saying service-policy output. As packets go out of this interface, we want to apply the policy p-voice. We want to compress those headers. And I think it's interesting that when I configure class-based header compression, the phone call stays up. You see, what is happening is that class-based header compression will not send compressed headers until it knows that the other side of the link can also send and receive compressed headers. However, over on router R1, let's say that we do not have the option of using class-based header compression. Rather, we need to use the older style of interface-based header compression. Let's see how to do that. On router R1, in global configuration mode, let's go into interface configuration mode. We'll say interface serial 0, and from here we will say IP RTP header hyphen compression. At this point, we have turned on RTP header compression on both ends of this link. The interesting thing is, if I went back right now to router R2 and did another show interface serial 0/0, we would not see the actual result of this RTP header compression just yet. Let me show you what I mean. On router R2, if I do a show interface serial 0/0, we started out at 25K. It looks like we've dropped down to 15K. That's some significant bandwidth savings. However, we're not done yet. You see, the way the show interface statistics work, they are based on an average over a period of time. By default, the show interface statistics are based on a 5-minute average. I have set this to use the minimum amount of time, which is only 30 seconds. Let me show you how I did that. If we take a look at the running configuration, and we go down to interface serial 0/0, notice this command, load-interval 30. This says that we want to be looking at 30-second averages as an output when we look at the show interface command. Let's do another show interface serial 0/0. Let's see how much we have dropped down. I think 30 seconds have now elapsed. Think about what has just happened here. We went from a point where a single voice call was taking up about 25 kilobits per second, and that has been reduced to only 10 kilobits per second. Let's say that we had 100 kilobits per second of bandwidth available for voice traffic. Before turning on RTP header compression, how many simultaneous voice calls could we place? If they took up 25K each, I would say only about 4 voice calls. However, after turning on RTP header compression, how many 10 kilobit per second phone calls can we complete with 100 kilobits per second of bandwidth available? That comes out to about 10 simultaneous phone calls. By turning on RTP header compression, we have more than doubled the call carrying capacity of this link. That's the power of RTP header compression. Let's go back out and review where we have been in this lab. In this lab, we took a look at header compression. We could do header compression either in the RTP or in the TCP environment. Our main focus was on RTP, however. RTP, that's what's used for our voice calls. We began by taking a look at the theory of header compression. We said that we weren't truly compressing the headers, rather we were making a copy of the header, and then we were caching that copy in the routers at each end of the link, because we made the observation that very little is changing during this phone call or during this TCP session. With that theory under our belt, we then took a look at how much bandwidth was being consumed by a phone call, and it looked like it was about 25 kilobits per second. Then we turned on class-based header compression on one of the routers, Remember, we have to be running at least iOS 12.2.13t to support class-based header compression. Then we went to another router and we said, let's imagine this router is running older iOS. Let's use interface-based header compression. With interface-based header compression, we're not able to be as granular as we can be with class-based header compression. With class-based header compression, we can say that we only want to compress the RTP or TCP headers for traffic that falls within a specific class of traffic. So for example, with class-based header compression, we may compress audio RTP headers, but not video RTP headers, or maybe G.729 audio headers, but not G.711 audio headers. We're not able to be as granular with the legacy approach, configuring RTP header compression in interface configuration mode. But both modes are compatible. We turned on RTP header compression on each end of this link with that voice call in progress. Then we took a look at the resulting bandwidth demand of that single voice call, and it dramatically dropped. It dropped from 25 kilobits per second for a single voice call down to only 10 kilobits per second for a single voice call. RTP header compression more than doubled our call carrying capacity.